All righty, good morning, lads and ladies. Welcome back to the wonderful world of Calc 2. Today, we are going to be continuing in our kind of recent charge of developing convergence tests for infinite series. So today we are going to actually meet two new tests. These are from section 11.4 in the textbook, and they are called the comparison tests. So without further ado, let me go ahead and flip on the document camera. And is Fabrice here yet? Let's see if I can update for him. There he is. All right. So what I was just saying, today we're going to continue developing more convergence tests for infinite series. Namely, today we're going to learn two tests called the comparison tests. And then I think Fabrice just popped in. I wanted to let you know that this afternoon I will have time to get in and remark your test with the updated work you sent me. So I apologize. I know it's been a minute. But I do actually have time this afternoon for the first time in several weeks to do something extra. So I will be going back and rescoring your test today, Fabrice. This is, of course, MAC2312, section 004, which is Calc 2. And the date today is the 2nd of March, 2022. Again, today, about the comparison tests. Which is section 11.4. The first of these is very, very similar to a test we learned for improper integrals, type 1 improper integrals. There was a comparison theorem in section 7.8. So I want to actually begin today, not by talking about infinite series, but by kind of jogging your memory about this very similar theorem. Start off by saying recall. In section 7.8, we learned this theorem. I said if 0 is less than or equal to f of x is less than or equal to g of x on the interval a to infinity, then two things are true. If the integral from a to infinity of g of x dx converges, that implies that the integral from a to infinity of f of x dx converges. So remember when we talked about comparing the areas under the curves, since the one fits inside the other, if the big one is finite, the small one must also be finite. The other kind of side of this coin was that if the integral of the smaller function, if the integral from a to infinity of f of x dx diverges, that implies that the integral of the larger function, the integral from a to infinity of g of x dx, also diverges. So this was the comparison theorem for improper integrals that we learned back in section 7.8. As we saw last time, improper integrals, specifically type 1 improper integrals and infinite series, are very, very similar. So similar, in fact, that there is a theorem nearly identical to this for series instead of for integrals. So the analogous result for series is called the direct comparison test. And this is the first new convergence test that we're learning today. There will be another one. There are two comparison tests for series. And I want you to just kind of compare the blue theorem up there from 7.8 to what we're going to say here. This says if 0 is less than or equal to an is less than or equal to bn for all n greater than or equal to some number a, then two things are true. If the sum from n equals a to infinity of the bn's converges, that implies that the sum from n equals a to infinity of the an converges. And if the sum from a to infinity of the an diverges, that implies that the sum from a to infinity of the bn diverges. So you see, these things are almost identical. In the 7.8 theorem, we had 0 is less than f of x is less than g of x. Here we have the same thing just for the sequences an and bn. Remember, sequences and functions, they're like the same thing. Sequences just have domain that is whole numbers. So we have some inequality for the functions from a to infinity. Here we have some inequality for the sequences from a to infinity. This n greater than or equal to a is the same thing as saying, from a to infinity. And then the conclusion has the same flavor. The sum of the larger guys being convergent forces the sum of the smaller guys to be convergent, right? The bn's are bigger than the an's. So it says if you add up all of the bn's and you get a finite thing, since the bn's are bigger than the an's, that means adding up all of the an's will give you a finite thing as well. On the other hand, since the an's are smaller than the bn's, if adding up all the an's gives you infinity, then adding up all the bn's would have to give you infinity as well. Again, because the bn's are bigger. So if you're bigger than something infinite, you are infinite. That's what this second line says here, right? The bn's are bigger than the an's. If the sum of the an's is infinity, then the sum of the bn's has to be infinity, because each term of the series over here is bigger than each term of the series over here. Or if you're smaller than something finite, you must be finite. Again, the an's are smaller than the bn's. So if when you add up all the bn's, you get something finite, you must get something finite when you add up all the an's. Every term of this series is smaller than the corresponding term of this series. So if this adds up to something finite, and everything here is bigger than everything here, then this must also add up to something finite. That's the logic. I'm not going to go through a full rigorous proof, but I will try to convince you a little bit, right? So we'll say it's a little proof sketch. Since an is less than or equal to bn, it follows that, say, a1 plus a2 plus a3 plus and so on is less than or equal to b1 plus b2 plus b3 plus and so on, right? This says a1 is less than b1. Also, a2 is less than b2. Also, a3 is less than b3. So this guy is smaller than this guy. This guy is smaller than this guy. This guy is smaller than this guy. Every term of the series over here is smaller than every term of the series over here, which means that the whole series here has to be smaller than the whole series here. And this thing on the left is sigma n from 1 to infinity of an. And the thing on the right is sigma n from 1 to infinity bn. So if this guy is finite, then this guy has to be finite, right? If you're smaller than something finite, you must be finite. On the other hand, if this guy is infinite, then this guy has to be infinite because this guy is bigger than this guy. And if you're bigger than infinity, you got to be infinity. That's the idea. I won't go any deeper than that. We could do a rigorous proof, but I don't want to get lost in the technical sauce. I want you to understand the feeling of the proof and the kind of meaning of the theorem. And then the main thing for us is learning how to use the theorem. So before I dive into examples here, are there any questions on sort of what the theorem, the comparison test is saying? Or the logic of the little baby proof I just went through? Okay, then let's go ahead and do it. Let's see if we can make use of this. I'll say this statement right here, the direct comparison test, this is one of our convergence tests. And so if you're doing that thing I suggested where you have a special page in your notes dedicated to convergence tests, this is what goes right after the integral test. All right, this is the next big important theorem from chapter 11 for us. So, or if you're making flashcards for your convergence tests, you should have a flashcard for this. All right, here we go. Let's investigate the convergence of the series S equals sigma n from 1 to infinity 1 over n cubed plus 2. Just for fun, I think it's always nice to write out a few terms of the series just so you can see what the hell it is you're working with. So the first term, the n equals 1 term, would be 1 over 1 cubed plus 2. 1 cubed is 1, so that would be 1/3 plus. The next term would be 1 over 2 cubed plus 2. 2 cubed is 8, so that's 1 over 8 plus 2, or 1/10. The next term, the n equals 3 term, would be 1 over 3 cubed plus 2. 3 cubed is 27, so that's 1 over 27 plus 2 is 1 over 29. And the next term, we'll do one more, would be 1 over 4 cubed plus 2. 4 cubed is 64, so it'd be 1 over 66. And it keeps going like that. We could try the test for divergence. That's an option. This will pass the test for divergence, though. Let me just kind of cycle through the tests we know and remind you how those work. So we could try TFD. What TFD says is if the limit of the ANs is not 0, then the series sigma AN must diverge. So TFD would say, okay, calculate the limit as n goes to infinity of AN let's see what that is. If that's not 0, then I learn the series diverges. The ANs here are 1 over n cubed plus 2. And as n goes to infinity, this is 1 over infinity cubed plus 2. Well, infinity cubed is definitely infinity. Infinity plus 2 is definitely infinity. This is 1 over infinity, which is 0. So what do we learn from the test for divergence? What is the result here? Very good. This is inconclusive. We saw last time that there are series where the AN go to 0 that diverge, and we've seen that there are series where the term goes to 0 that converge. It could go either way. So TFD, our kind of easiest test, unfortunately on this series is inconclusive. This is definitely not a geometric series, right? This is not some constant raised to the n, and there's no algebra I could do to make it look like that. The series does not telescope that denominator. It does factor, but it's not a pleasant thing to factor. So I'd say this is not geometric. Probably not telescoping. And integrating f of x equals 1 over x cubed plus 2 is difficult. Not impossible. We could integrate this function and use the integral test. It's easy enough to show that this is a decreasing function. It's positive on the interval 1 to infinity, and it is continuous on all positive real numbers. But the integral that you'd have to do for the integral test is unpleasant. So TFD is inconclusive, and none of our other tests are worth trying. So we're going to use the new one. We're going to use the direct comparison test. Which in the future, by the way, I will abbreviate as DCT. So DCT says, if you think the series converges, try to find a bigger series that's easy to show converges. And then you can conclude that your series converges. If you think your series diverges, try to find a smaller series that's easy to work with. And then you can conclude that your series diverges. In other words, we need to come up with an inequality. And the type of inequality we're going to come up with depends on whether we think the series is convergent or divergent. So based on what we've said so far, like looking at the first few terms, looking at the AN, what do you think? Do you think this is a convergent series or a divergent series? What's your intuition? Guesses are okay. Just tell me what you think. Got one response so far. Anybody else got a feeling? Okay, any other thoughts? So far it's competitive. We don't have a consensus yet. I'd like to see more thoughts. Okay. Yeah, I've got more votes for convergent than I do for divergent. So remember the way this works. What is required for a series to converge is that the terms of the series, the AN, go to 0 and go to 0 quickly, right? Like we need the general term of the series, the thing you're adding up, to get really, really small, really, really fast. That's what TFD says. TFD says if you don't get small, if you don't go to 0, then the series has no chance of converging. But even that isn't enough. You need to go to 0 fast. Like 1 over n, not going to 0 fast enough. 1 over n squared, that is going to 0 fast enough. 1 over n cubed. If the 2 wasn't here, what could you tell me about this series? Very good. If not for this 2, if this was just sigma 1 over n cubed, that would be a p series with p equal to 3. So it would be a convergent series, right? Because a p series where p is bigger than 1 is a convergent series. So that leads us to believe that this is a convergent series because it's very, very similar to the 1 over n cubed series. The only difference is this one has a little +2 down here. So we're going to try and structure our inequality to make use of this fact. So I want to sandwich my guy in the middle underneath something else that I know to give a convergent series when summed. And the natural choice here, like we were saying, this is very similar to 1 over n cubed. Let me show you how we'll cook this up. We would say that n cubed plus 2 is greater than or equal to n cubed. Let's say observe. Right? Certainly that's true. If you add 2 to something that's bigger than the thing you started with. And this implies that 1 over n cubed plus 2 is less than or equal to 1 over n cubed. Right? So when you take reciprocals on both sides of an inequality, the sense of the inequality flips over. If a is bigger than b, that means 1 over a is smaller than 1 over b. And the other thing that's true here, these are positive, right? As long as n is bigger than 1, these are definitely going to be positive. So this is true for all n greater than or equal to 1, certainly, which is where I'm summing. I'm summing from 1 to infinity. We can say also the series of the bn over here, the bigger guys, from 1 to infinity, sigma 1 to infinity, 1 over n cubed, is a convergent p series. Because p here is equal to 3, which is bigger than 1. So this inequality is what's going to do the job for us, right? This is sort of the secret sauce here. The terms of my series are smaller than the terms of this convergent p series. Therefore, by our inequality and the direct comparison test, the series S equals sigma n from 1 to infinity, 1 over n cubed plus 2 must also converge. So take a look at the logic we're employing here and make sure you are very, very comfortable with it, right? Here's the full solution. See if there's anything there that is uncertain. See if you can tell where we're connecting the dots and where we're using the theorem. Questions on what we've done here. So any questions on what we're saying here, where we get this inequality, why this inequality is useful, how we know this series converges, or how we connect the convergence of this series to the convergence of our series. The idea is our series is smaller than this series. And since this series is finite, our series must also be finite. Let's try another. Let's investigate. Investigate the convergence of S equals sigma n from 2 to infinity 3 over the square root of n minus 1. Again, I think it's nice to write out the first two terms of the series just to get a feel for what it is we are looking at. So the very first term of the series would be 3 over the square root of 2 minus 1. That's 3 over the square root of 1. The next term would be 3 over the square root of 3 minus 1. That's 3 over the square root of 2. The next term would be 3 over the square root of 4 minus 1 is 3 over the square root of 3. And we have 3 over the square root of 5 minus 1, 3 over the square root of 4, and so on. Again, there are other tests we could try. We could try TFD, we could try the integral test, definitely not geometric, definitely not telescoping. I'm just going to jump to the comparison because that's what we're going to do here. If I try to use the direct comparison test, I need to construct an inequality. And when I go to build that inequality, it's very helpful for me to think whether I believe the series converges or diverges. So sort of, what series is this most similar to? If you look at these terms, what does this remind you of? If this minus 1 wasn't down here, this would just be 3 over the square root of n, right? Which is almost a p-series. It's a constant multiple of a p-series. So here's what I would say. First, observe that n minus 1 is less than or equal to n. That's definitely true. So the square root of n minus 1 is going to be less than or equal to the square root of n. Right? If a is smaller than b, then the square root of a is smaller than the square root of b. It's because the square root is an increasing function. Which implies that 1 over the square root of n is less than or equal to 1 over the square root of n minus 1. Right? This is absolutely true because root n is larger than root n minus 1. 1 over root n is smaller than 1 over root n minus 1. This sort of inequality work is the main skill that we're going to be practicing here. Now, if I multiply this guy by 3, he will turn into the thing inside my series. That's what I want. I want my thing to show up in this inequality. And when I multiply this by 3, it gets bigger. So we say, hence, we arrive at the inequality. My goal is to build something that looks like the inequality in the theorem. Right? 0 is less than or equal to an is less than or equal to bn. Well, 1 over root n, that is going to be positive. That's always going to be greater than or equal to 0. 0 is less than or equal to it, 1 over root n. And this thing is already bigger than 1 over root n. If I multiply it by 3, it's going to get bigger still. Actually, and this is true for all values of n that the inequality makes sense. This is true for all n greater than or equal to 2. The idea here is that multiplying by 3 only makes this bigger. It only makes the inequality more true. You can finish the problem by saying, moreover, the series sigma n from 2 to infinity 1 over the square root of n might not look like it, but this is a p-series. This is sigma n from 2 to infinity 1 over n to the 1/2 power. This is a p-series. P equal to 1/2. 1/2 is less than or equal to 1. So this series diverges. Right? P series converge if P is bigger than 1. P series diverge if P is less than or equal to 1. So what we have here is this inequality. So the magic inequality for this problem. And I know that the series that we get by summing this, by slapping a sigma onto this thing, is divergent. So the terms of this divergent series are all smaller than the terms of my series. Therefore, our series S equals sigma n from 2 to infinity 3 over the square root of n minus 1 must also converge. So again, I'd like you to take a second, look at your notes, make sure you have everything written down cleanly. The words are important here, maybe at least as important as the math symbols. There's very little calculation. It's all about the logic. So take a second, look at your notes, look at what I have here, and ask questions. Let me know what you're thinking, anything, even if it's just what the fuck, anything at all. Let me know what's in your brain. Any thoughts on this? It's actually pretty straightforward, right? All the hard work is in coming up with the inequality. Okay, I'm going to do one more example like this, and then we're going to talk about a different kind of, well, two more examples. We'll talk about a different kind of test. Good, okay, that's good. So what do we need to get credit on the test? You need to cook up this inequality, and you need to tell me for what values of n that inequality is true. Then you need to perform the actual comparison. You need to tell me, okay, well, here's the terms of my series. So I'm comparing to this. So you need to tell me whether the thing that you get when you turn this into a series by slapping a sigma on it, when you sum that, is that convergent or divergent? The inequality says the terms of my series are larger than this thing. So if the series I get when I slap a sigma onto this is divergent, that will tell me that the sum of these things is divergent. So the parts you need, the inequality. You need to tell me the inequality, you need to tell me where the inequality is true. Then you need to tell me whether the series you're comparing with is convergent or divergent and why. So telling me that the sigma 1 over root n is a divergent p series, necessary. And then finally, you need your conclusion here. You need to say, therefore, our series also diverges. So those would be the individual parts. The minimal solution here would be this, and then everything down here. And we'll work at the top. And this is us coming up with that inequality. It's a lot like the squeeze theorem from Calc 1, or the squeeze theorem problems that we did when we were in 11.1 talking about sequences. It's up to you how much work you're going to show coming up with your inequality. Right? Building this inequality, that's most of the work, but what you're going to write down as you come up with that inequality is kind of up to you. Whatever you need to in order to figure it out. Once you have your inequality, it's just a matter of saying whether the series you're comparing with is convergent or divergent, and then concluding the correct thing, that your series either converges or diverges based on the inequality. Okay. Let's try one more. Okay, investigate the convergence. S equals sigma n from 1 to infinity, 1 over 2 to the n plus 1. Again, I'll write out the first few terms of the series. Always nice to do that. So this is 1 over 2 to the 1 plus 1. That's 1 over 2 plus 1, or 1/3. Plus 1 over 2 to the 2 plus 1. That's 4 plus 1 is 1/5. Plus 1 over 2 to the 3 plus 1. Well, 2 to the 3 is 8. So 3 plus 1 is 1. 8 plus 1 is 1/9. Plus 1 over 2 to the 4 plus 1. Well, 2 to the 4 is 16. So 16 plus 1 is 17. So it's plus 1, 17. And it goes on and on and on like that. So I want to know, does this series converge or diverge? And like all these other problems, what you want to do is kind of ask, is there a series that is very similar to this one, but easier to work with? That's correct. Yep. So what is the series that is easy to work with, that is very similar to this one? Very good, right? If not for this plus 1, if this was just sigma 1 over 2 to the n, that's a geometric series, right? That was actually the very first series we worked with. And this guy is so close to that. The only difference here is a plus 1, right? The 1 over 2 to the n series is 1/2, plus 1/4, plus 1/8, plus 1/16. The only difference here is that these denominators are 1 larger, which makes each one of these terms smaller. Bigger denominator, smaller overall. So we can compare this nicely using the direct comparison test with the series 1 over 2 to the n. We want to go back for a second. Yeah, I can go back for just 1 second. Okay. Just the last one. So the idea for all of these is that you want to look at the series that's given to you and ask, what very simple series is this most similar to? That's what you're going to compare against. So if there's like a plus 1 or a minus 1 or a constant multiple, something like that, then kind of pretend like those aren't there. What series do you get when you ignore those little superfluous things? That's the guy you're going to compare to. So here, like multiplying by 3 upstairs, that doesn't really change much. Subtracting 1 downstairs, that doesn't really change much. This thing is very, very similar to 1 over root n. So right away, we had in our head that I want to compare this series to the sigma 1 over root n series. To do that, we had to build this inequality. In the new problem, the sort of superfluous stuff, the stuff that doesn't really change much, is this plus 1 down here, right? With or without that, this series is very, very similar, right? The only difference is that it would be 1/2 plus 1/4 plus 1/8 plus 1/16 without the plus 1. So the plus 1 doesn't change the behavior very much. So we're going to try to compare this to the series sigma 1 over 2 to the n. And to do that, we need an inequality. So we know that 2 to the n plus 1 is bigger than 2 to the n. Which implies 0 is less than or equal to 1 over 2 to the n is less than or equal to, no, sorry, 2 to the n plus 1 less than or equal to 1 over 2 to the n. And this is true for all, it would be true for all n greater than or equal to 0, but I just care about n is bigger than or equal to 1. Right? So like 1/3 is smaller than 1/2. 1/5 is smaller than 1/4. 1/9 is smaller than 1/8. There's my inequality. Okay. Also, the series sigma n from 1 to infinity 1/2 well, we can write this as sigma n from 1 to infinity 1/2 right? 1/2 is the same as 1/2 is a geometric series with r equal to 1/2. So the absolute value of r is the absolute value of 1/2 is 1/2, which is less than 1. The idea is that my series here is not a geometric series. The original series I was given is not geometric. This thing, not geometric. But it is very similar to this series, which is geometric. Now, this geometric series has common ratio 1/2. Since the absolute value of that common ratio is less than 1, the absolute value is this, which means sigma n from 1 to infinity 1/2 converges. Hence, therefore, our inequality and the direct comparison test, the series that we're working with, S equals sigma n from 1 to infinity 1/2 plus 1, must also do what? What's the final word of this solution? Cool. Yeah, must converge, right? Must also converge. Our series, this series, has terms that are all just a little bit smaller than this series. And since this series is convergent and my series has terms that are smaller, my series must also be convergent, must also converge. So this is the last example I'm going to do with DCT. A word of warning, right? I've said this a few times. WebAssign, you just click converge or diverge. You got a 50-50 chance of guessing correctly. And if you get it wrong the first time, there's a 100% chance you'll get it right the second time. Answering the questions correctly in WebAssign is not a measure of your understanding. It's very easy to answer those questions correctly, but have no idea how to write out an argument like this. You got to practice writing out arguments like this. As you solve the homework problems, anytime you're doing a direct comparison, you need to come up with an inequality like this, and you need to understand where it comes from. You need to write in full sentences a logical argument that gets you from something about the series you're comparing with to something about the series you were asked about in the first place. And that logic needs to be solid. It needs to follow from the inequality and the statement of the theorem. If you're ever uncertain as to whether the thing you've written out is a good solution, right? Like you click the button, you get the right answer, but you're not sure the thing on your paper would be 100% on the test, then you should ask me about it. Please ask a classmate about it. Use the Discord. Post pictures of your solutions, ask each other about them, send pictures of your work to me, ask me about it, come to office hours, all that stuff. But please don't let WebAssign trick you into thinking that you're doing everything right just because the green check comes up. Make sure that you really do have good solutions for these. Otherwise, the test will bite you hard in the butt. That's a great question there. So Mohan asks, should we only use DCT if there is a very similar P-series or geometric series? Basically, yeah. Now, depends on what you mean by similar. So maybe before we move to LCT, let me do one quick new example, slightly different example. Again, it depends on what you mean by similar. So here's an example where the original series kind of looks like it has some geometric-y stuff and kind of looks like it has some P-series-ish stuff. I'll tell you, this is a convergence series. And there's a few ways you could attack this. E to the negative n, that's 1 over e to the n. And it's definitely smaller than 1 for all n greater than or equal to 1. So e to the negative n over n to the 3/2 would be less than or equal to 1 over n to the 3/2. So we could do a comparison here against this P-series, sigma 1 over n to the 3/2. That's an option. But also note that e to the negative n over n to the 3/2 is the same as e to the negative n times 1 over n to the 3/2. And since 1 over n to the 3/2 is also less than 1, we could say this is less than or equal to e to the negative n. i.e., we get the inequality 0 is less than or equal to e to the negative n over n to the 3/2 is less than or equal to e to the negative n. So we could also compare with the series, the geometric series, sigma e to the negative n, sum from 1 to infinity. So yeah, usually we're going to compare with a P-series or a geometric series, because those are the two kind of families of series that we know the most about. Those are the two families of series where we can most quickly say whether they converge or diverge. They form our standard basis for comparison. But exactly what similar means in this context is not 100% concrete. Similar could mean a lot of different things. Sometimes these inequalities are quite sharp, meaning the thing you're comparing against is like almost the same as the thing that you're working with. Sometimes they're quite sloppy, right? Like saying that e to the negative n over n to the 3 halves is smaller than 1 over n to the 3 halves is a really big understatement. It's way smaller than 1 over n to the 3 halves. But either one of these approaches would work. I'm not sure if that feels like a satisfying answer, but I guess what I'm trying to say here is that it's not accurate to say that this series is similar to this series. They share some characteristics, namely the n to the 3 halves downstairs. But the terms of this series are much, much, much smaller than the terms of this series. They're really not similar beyond having that like algebra similarity. But either comparison would work. I would say the bottom one is a closer facsimile. All right. So that fun diversion aside, I want to ask you another question. And I'll just phrase it like this. We're not going to be able to solve this right away, but I'm going to give you the question. We're going to investigate the convergence of the series a lot like the one we did a second ago. Sigma n from 1 to infinity, 1 over 2 to the n minus 1 now instead of plus 1. It would be accurate here to say that this series is very similar to the 1 over 2 to the n series. However, we run into a problem if you try to use direct comparison. One over 2 to the n minus 1 is not less than 1 over 2 to the n. In fact, the other inequality is true. 1 over 2 to the n is less than 1 over 2 to the n minus 1. Right? So this guy has a smaller denominator than this guy, which makes him bigger overall. Try plugging in some numbers. When you plug in 1 for n, this is 1/2. This is 1. You plug in 2 for n, this is 1/4. This is 1/3. So the terms of my series here are not smaller than the convergent geometric series, 1 over 2 to the n. They're larger than that guy. And if you look back at what the comparison test says, direct comparison test says If your terms are smaller than the terms of a convergent series, then your series converges. And if your terms are larger than the terms of a divergent series, then your series diverges. What if your terms are larger than the terms of a convergent series? Because that's what we have here. The terms of my series, 1 over 2 to the n minus 1, is bigger than 1 over 2 to the n. 1 over 2 to the n is smaller. Does this test apply? Is there anything I can use here? Let me say this another way. Our series is bigger than a convergent series. Does that teach us anything? R, OUR, R series. So what the direct comparison test says is if you're smaller than a convergent series, you're convergent. And if you're bigger than a divergent series, you're divergent. But what if you're bigger than a convergent series or smaller than a divergent series? You see, there's two possibilities that are not discussed in the comparison test. And both of those are inconclusive. So being bigger than a convergent series, this doesn't tell us anything. Doesn't tell us anything useful. Which is why we have something else called the limit comparison test. You see, what I would really like to say is that because the terms of this series are so close to the 1 over 2 to the n series, that this series should converge. Unfortunately, this series is not smaller than this series, it's bigger, but it's bigger by only a tiny, tiny bit. So the fact that this guy is finite and this guy is just a tiny bit bigger than him should be enough for me to say that this guy converges. But what do you mean by a tiny bit? We need some specific way of saying how similar two series have to be in order for them to share the same convergence behavior. And that's what the limit comparison test does. It gives us a condition that says, if these two series are like at least this similar, then one converging automatically makes the other converge. One diverging automatically makes the other diverge, regardless of which way the inequality points. So the inequality, the natural inequality we construct from this guy, points in the wrong way for the direct comparison test to be useful. And for those sort of situations, we have this other comparison test called the limit comparison test. What this says is, if sigma an and sigma bn. I'm going to leave off the bounds because it doesn't matter. Are series with positive terms and we're going to cook up this number c as the limit n to infinity an over bn, and this number is both strictly positive and finite. Meaning not zero, not infinity. Couldn't possibly be negative because the an and the bn are all positive term things. If that limit is both strictly positive and finite, then sigma an and sigma bn do the same thing. They converge or diverge together. i.e., they do the same thing. Hold on 1 second, I'm sorry. Hello? 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 So the limit comparison test says, if you think two series are similar, then go ahead and calculate the limit of the an over the bn. If that number comes out positive and finite, then those two series really are similar. They really do the same thing. If one converges, the other converges. If one diverges, the other diverges. I want to sketch a quick proof for you here. Just try to see why this is true. So let's suppose the limit as n goes to infinity of an over bn is equal to c, where 0 is less than c is less than infinity, right? C is positive and finite. This means, what does it mean to say that the limit of something is equal to c? Well, it means that as n gets bigger and bigger and bigger and bigger, that thing gets closer and closer and closer and closer to c. So this means that an over bn gets closer and closer and closer to c as n gets bigger and bigger and bigger and bigger. In other words, an over bn is very close to c for large values of n. If you multiply on both sides by bn, then this becomes an is approximately equal to c times bn. And now if you sum on both sides, sigma an, the sum of the terms an, must be approximately equal to, pop out the constant, c times sigma bn. So if one of the series is finite, then the other one must be finite. And if sigma Bn is infinite, so is sigma An. That's it. That's the proof. So if the limit of the An over Bn is some positive finite constant, then the series sigma An is basically that constant times the series sigma Bn. Really, really close enough to that if one is finite, so is the other. If one is infinite, so is the other. All right. This limit comparison test here, this is your next convergence test. So if you're making flashcards or you have that special page in your notes, you should have the test for divergence. You should have the theorems on geometric series and telescoping series. You should have the integral test, the direct comparison test, and now this, the limit comparison test. This is your next important convergence test. Let's go ahead and use it to answer that last question, and I'll wrap up there. So now we return to this example. Investigate convergence of sigma n from 1 to infinity, 1 over 2 to the n minus 1. Yeah, if you're creating a list of convergence tests for infinite series, which I strongly encourage you to do, have a special page in your notes for all the convergence tests. So far, there will be more, but so far you should have the test for divergence, our theorem on geometric series, our result on telescoping series, like how do you handle telescoping series, the integral test, the direct comparison test, the first new theorem we had today, and now this one, the limit comparison test. So you should have 6 kind of convergence theorems for series so far. Yeah, this is exam 2 stuff, yeah. Exam 2 will be after spring break, the week we come back, either Wednesday or Friday, the week we come back, probably Friday. All right, so let's go ahead and get into this. What we're going to do is run the limit comparison test. And the way this works is you have to start by picking your BNs, right? AN is this thing. AN is 1 over 2 to the n minus 1. Your limit comparison test, you pick BN to be the thing that you think is similar to AN. There's no inequalities here. You just pick BN to be the thing that you think is very similar to your ANs, whose series is easy to work with. And then you calculate that number C, which would be the limit as n goes to infinity of AN over BN. Which is the limit as n goes to infinity. AN here is 1 over 2 to the n minus 1. Dividing that by 1 over 2 to the n. A little bit of algebra. We flip and multiply by the bottom, and that gives me 2 to the n over 2 to the n minus 1. All right, you have this top. And then you flip and multiply by this. So that would be 2 to the n over 1 times 1 over 2 to the n minus 1. That's just 2 to the n over 2 to the n minus 1. We need to take the limit here as n goes to infinity. If you plug in infinity, the top is infinity, the bottom is infinity minus 1. That's also infinity. You can use L'Hopital's rule if you want, or you can divide top and bottom by 2 to the n. Renormalization trick from 11.1. 2 to the n times 1 over 2 to the n upstairs is 1. Distributing 1 over 2 to the n downstairs, remember the top and bottom fractions always in parentheses. That would be 1 minus 1 over 2 to the n. As n goes to infinity, 2 to the n goes to infinity. So 1 over 2 to the n goes to 0. So this is 1 over 1 minus 0, which is just 1. We ask ourselves, is this positive and finite? Well, 1 is positive. It's a positive number. 1 is finite. Yep, for sure. Definitely 1 is finite. So we say since C equals 1 is positive and finite, the two series sigma an, which is sigma 1 over 2 to the n minus 1, so from 1 to infinity, and sigma bn, which is sigma from 1 to infinity, 1 over 2 to the n, they do the same thing. They converge or diverge together. I'm not done yet, though. All I've shown so far is that these two series do the same thing. Remember my goal. My goal is to tell you whether the series that we started with, this series, sigma an, converges or diverges. And so far what I've shown is that this series does the same thing as this series. So if I can prove that this series diverges, then I will learn that my series diverges. If I can prove that this series converges, I will have shown that my series converges. What we need to do to finish the problem is say what this series does. Then we can conclude that my series does the same thing. The way I like to phrase this is, moreover, sigma 1 over 2 to the n, we already did this earlier, sigma n equals 1 infinity 1 over 2 to the n, is a convergent geometric series, right? Because the absolute value of r is 1/2, which is less than 1. Therefore, by the limit comparison test, our series sigma 1 over 2 to the n minus 1, so from 1 to infinity, must do the same thing, right? That's what we proved up here, that these two series do the same thing. Since this series converges, our series must also converge. And that is the end of the problem. So again, you notice most of the work is words, right? There is some calculation here. We had to calculate a certain limit, but most of the work here is words. And you need to write the words, right? As you practice this stuff, without the words, there ain't shit here. Literally. Like most of the math here is the words. As you get higher and higher and higher up in mathematics, you find that this is true. I can maybe show you one day just for fun some of the research that I've done. There is calculation in there, but there's a lot of like language, a lot of writing It's logic. It's logic. That's what we're doing here. We're employing this theorem called the limit comparison test to get from a result about one series that's easy to a result about another series that's less easy to work with. So this is where I'm going to stop for today. It's right here. We've done plenty of practice with the direct comparison test, little practice with the limit comparison test. I have a new homework for you queued up and ready to go. It's going to pop open here in just a few minutes. That homework set has stuff from 11.4, which is what we've covered today, and stuff from 11.5, which we're going to cover on Friday. So on Friday, I will come back in. We'll do a few more practice problems with the limit comparison test on Friday, and then we're going to talk about something new called the alternating series test. And that's where we're going to have an estimation theorem as well. So Friday is a big day. I know it's the last class day before spring break, but please do not miss class on Friday. The estimation theorem on the alternating series is the only estimation theorem I require you to learn. And it's one of those things that if you don't learn it, there's going to be a problem on the test where you're just completely dead in the water. And I don't want that to happen to you. Calculations will get more challenging. They won't all be this easy. Right now, I'm trying to keep the calculations very easy because I want you to pay attention to the logic. But as we wade deeper and deeper into these waters, I will slowly use more and more complex calculations like L'Hopital's rule stuff, trig stuff, slightly more complex algebra, things like that. But generally, the calculations here are not terrible. Not terrible. It's mostly about the logic. Other questions here as we wrap up? Alrighty then, I'm going to go ahead and end the meeting. I hope you guys have a lovely rest of your day. Do take a look at that WebAssign homework. If you haven't finished the 11.3 stuff, please finish that as soon as you can. That's going to close on Friday. And then if you have finished that, please take a look at the new one, the 11.4 and 11.5 stuff. I'm going to set it to be due on Monday of next week, but I'll probably change that because I know Monday of next week is the start of spring break. And it wouldn't be nice to have homework due then. You are going to have shit to do over spring break, just to let you know. Like, I'm going to give you an assignment to work on because I really don't want you guys falling behind over the break. That would be really, really bad. Exam 2 is going to be the first week after you come back from break. So again, don't like slack over break. If you don't do any of this shit over break, you're going to come back and be fucked on that test. I really don't want that to happen to you guys. Talk to me if you're having trouble, if this is feeling hard, if you're nervous about anything, please reach out and let me know what's going on. Yeah, that's the case for me. So this exam structure for test 2 will be the same as for test 1, all the same rules. And if you do end up, needing a little more time to prepare, of course, you can let me know. But that test again is going to be the week we come back from break. So there's quite a bit of time between now and then to study. Please do study hard. But yeah, as always, if you're in trouble or whatever, reach out to me. Let me know. I will work with you. That's it. So I will see you guys on Friday when we talk about more limit comparison and alternating series. Take care.